Hey guys, welcome back to Between Whiles. Today we're going to talk about one of those questions that are very common in cosmology and astrophysics. It's certainly one of those questions that I get the most when I go to any sort of social gathering, and it's what's the size of the universe? It's certainly not an easy question to answer, and it actually depends on what exactly you mean by the size of the universe. First of all, let's separate these into two questions. The first one is, what's the size of the observable universe? That is, the universe we can interact with, the universe we can actually see and measure. The second question is, what is the size of the whole universe? Which is probably why you clicked on this video. I'll try to convince you that the first one is a bit more interesting and has some important implications. We define the observable universe as the universe we can measure, the universe we can get light or any sort of information from. Outside of that boundary, we don't see anything else, not because there's nothing there, but because we can't really measure or see anything. And that's because of two important reasons. First, the universe has a finite age. As we understand in cosmology, time and space were created in the Big Bang. Because
our whole universe was in a hot, dense state that nearly 14 billion years ago expansion started.
Yes, the theme song of the Big Bang Theory got it right. The best current estimates of the age of the universe are 13.8 billion years. Second, the speed of light is finite, 300,000 kilometers per second, which means light from distant objects takes time to get here. Taking those things into account, we can measure a size of that observable universe. In principle, you would think, well, if you just convert that into a distance, that would give you that the edge of the observable universe is 13.8 billion light years away. But that's not true. The universe has been evolving differently during different stages of its life. At some point it was dominated by matter, at some point it was dominated by radiation, right now we are dominated by something we call dark energy, which makes the universe expand. If you take all those things into account, you work out that the actual size of the observable universe is going to be 46.5 billion light years away, which is equivalent to 93 billion light years across. I think it's pretty safe to say that that's pretty fucking big. So to summarize, you start with the age of the universe, you work out the distance, taking into account expansion and evolution of the universe, and you get to that distance. So the edge that limits that observable universe is what we know in cosmology as the particle horizon, because it denotes the horizon from which any particle throughout the history of the universe could reach us. So for the sake of argument, let's say that APA can travel at the speed of light. You would think that it would just take APA 46.5 billion years to get to the edge of the observable universe. Well, that would be true if the universe stopped expanding, if the universe out of a sudden stopped evolving. But that's not our universe. The universe keeps expanding. There's a distance in which things will actually move from us faster than the speed of light, which means that even with APA traveling very fast at the speed of light, he wouldn't be able to catch up with that space. How is that possible if things cannot move faster than the speed of light? Well, things cannot move faster than the speed of light in space, but that doesn't stop space from expanding faster than the speed of light itself. This doesn't violate any of the fundamental principles in physics. So here it's important to introduce a new horizon, one that denotes the limit of the things we can eventually interact with in the future if we were able to travel at the speed of light. And that one is called the cosmic event horizon. That's the one where if APA started the journey right now, traveling at the speed of light, that's the limit of the furthest thing he could ever reach. That one evolves as well because the universe is expanding. The size of the cosmic event horizon is actually smaller than the observable universe, which is something we need to wrap our heads around. Our best estimates of the size of that cosmic event horizon is that it's 16 billion light years, or 32 billion light years across. This implies that there are galaxies we see right now which are within the observable universe but further than our cosmic event horizon. Those galaxies are going to eventually disappear from our sight. So they're sort of like ghosts. That's just because they're moving away from us faster than the speed of light, so our cosmic event horizon cannot catch up with them. And that's a bit scary. That means that a lot of the universe we see out there will eventually be lost from our sight, and we will never ever be able to interact with those galaxies if we can travel faster than the speed of light. Because of the expansion of the universe, the cosmic event horizon is shrinking, which means we're seeing less and less of the universe as time goes by. So that's why this event horizon is a useful quantity, a useful horizon for us to think about, because it's the one that in practical terms we'll be able to travel to, or at least communicate with. Just as a side note, all the spheres I'm talking about are spheres in which we are the center. And that's just because of perspective. Any other civilization will have their own observable universe and their own cosmic event horizon. It's possible that some aliens with great technology are trying to get to us, but for them it's impossible because their cosmic event horizon is shrinking and we're outside that event horizon. That's perfectly possible. Okay, I told you this was a bit difficult, right? Now that we're done talking about the observable universe and the event horizon, we can go back to the question that you were probably wondering when you click on this video, and it's, what's the size of the whole universe? So to put it simple, we don't know for sure, but we do know a lot about physics and cosmology, which gives us hints. We expect the whole universe to have some sort of curvature, and that's one of the terms in Einstein's equations. You take into account the curvature. With our best measurements, we found that the curvature is actually 0, meaning the universe is flat. The implications of a flat universe is that it is infinite. But there are some uncertainties in those measurements. We don't know for sure if the universe is fully flat. It could be that the universe is so big that it seems to be flat, but it's actually slightly curved. If the universe happens to have an open geometry, that will mean the universe is infinite, just like it is when the universe is flat. But if the universe is closed, that would imply that the universe is finite. However, for all we know, the universe seems to be infinite. So to summarize, the size of the whole universe seems to be infinite. However, in practical terms, it's better to talk about two other horizons. One of them is the observable universe, which is 46.5 billion light years away from us. The second one is the cosmic event horizon, which is actually more useful because that's the one that we could ever possibly interact or communicate with. That one is 16 billion light years away. I hope you guys enjoyed the video. If you have any questions, please leave it in the comments below and subscribe to my channel for more astrophysics. Thanks.